Hello everyone and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about RL circuits, circuits that have resistors and inductors. So our objectives include applying Faraday's law to a simple RL series circuit to obtain a differential equation for current as a function of time, solving the differential equation for the current as a function of time using that separation of variables technique that we've used a couple times, calculating the initial transient and final steady-state currents through any part of that simple series and parallel circuit containing an inductor and a couple of resistors, and finally being able to sketch graphs of the current through or the voltage across the resistors or the inductor in these simple series and parallel circuits. So all about circuits that have resistors and inductors in them. So let's start off with our analysis of these circuits. When the circuit is first turned on, the inductor opposes the current flow and it acts like an open circuit. Contrast that to the capacitor, where when you first turned it on, it acted like a wire. Now, after a long time, the inductor keeps current going and it acts as a wire, it acts as a short. Contrast that with the capacitor, which after a long time, it acted like an open. They're opposites. Now, after a long time, if you remove the battery, the inductor is then going to act as an EMF source to keep the current going. So you can almost think of an inductor as something that likes to oppose change. If there's no current flow in the circuit, it doesn't want current flow. But after you eventually get it going for a while and you stop the current flow, it wants to keep it going. As the resistor dissipates power, of course, the current will decay exponentially to zero as you use up that energy. So, standard RL circuit diagram, our source of potential difference, resistor, and our inductor. Something important to note here, as we go through these analyses, the electric field inside that inductor is zero. All right, let's take a look at the current in the RL circuit. The first thing I'm going to do is I'm going to define a couple things. Let's talk about our current flow. Let's say it's in that direction. Let's also note our electric fields in here. If this is our source of potential difference, positive and negative side, we know the electric field points that way in there. Our electric field is going to go in this direction through our resistor, and inside our inductor, keynote, electric field is zero. Now, when analyzing these sorts of circuits, lots of people like to use Kirchhoff's voltage law. They like to say, as you go around here, minus V plus IR plus the voltage across the inductor equals zero. And although you can get the right answer doing that, it's not technically correct because Kirchhoff's voltage law is really just looking at items where you have a non-changing magnetic flux. Because you have a non-changing magnetic flux, we have to go back to some of these first principles. And we're going to start there and do this the more correct way. So let's start by writing our equation. The integral over the closed loop of E dot dl is going to be the opposite of d phi b dt. We've been doing that for a while, Faraday's law. Well, when we do this, let's look at our E dot dl side. We're going to have minus V plus our potential drop across R, IR. So minus V plus IR equals, and we know that d phi b dt is just going to be minus L di dt. We showed that in our last lesson. So that's how we set up our equation to get going here. So let's start to rearrange this a little bit. We have I minus V over R must equal minus L over R di dt as we work to separate our variables in our differential equation. Which implies then that, we have, as we separate these, di over I minus V over R must equal minus R over L dt. So the integral from I equals 0 to some final I must equal the integral from t equals 0 to some final value t. Okay, starting to solve this. du over u, that form, the integral of that is going to be the log of u. So the left-hand side is going to look like the natural log of I minus V over R, evaluated from I equals 0 to some value I, equals, and the right-hand side, of course, just becomes minus R over L t. All right, expanding out this left-hand side, substituting in our limits, that implies then that the log of I minus v over r minus the log of minus v over r must be equal to minus r over L times t. And the difference of the logs is the log of the quotient. Therefore, we could write the left-hand side is the log of I minus v over r divided by minus v over r equals minus r over L t. Once again, this natural log is pestering me. So let's raise everything e raised to those powers on both sides so that we can get rid of our natural log. And we can write the left-hand side as I minus v over r divided by minus v over r must be equal to e to the minus r over L times t. Or doing a little bit of algebra here, we'll multiply both sides by that minus v over r, so that the left-hand side, it becomes I minus v over r equals minus v over r e to the minus r over L t. Or going a step further, I equals, well, if we add that v over r to that side, we're going to get v over r, and if I factor that out of the right-hand side, it'll be 1 minus e to the minus r over L times t. I equals v over r, that current that you would get if you didn't have the inductor, times the quantity 1 minus e to the minus r over L t. So there's our current flow as a function of time. Now, when we talked about RC circuits, we talked about a time constant tau, which was equal to R times C. When we're talking about RL circuits, our time constant, which we still call tau, is now L over R. So we could write this then in the form I equals v over r 1 minus e to the minus t over tau. So it fits that same basic form of the solution that we saw previously when we were dealing with RC circuits. Once again, though, we're dealing with something 1 minus e to the minus t over the time constant, or e times minus e raised to the minus t over the time constant. You're going to see that form again and again and again. So there's the current. Let's take a look at the voltage.